Alright, so we'll start a lesson on two-dimensional and really I say and three-dimensional kinematics because there are some relationships between two-dimensional and three-dimensional kinematics. If you can do a two-dimensional problem, you can ultimately do a three-dimensional problem really just about as easily in kinematics. The key thing to remember about two-dimensional and three-dimensional kinematics is the idea of independence of motion. That what happens in one dimension or one direction does not affect what happens in another direction or another dimension. So in this picture here I have a red ball which has been dropped straight down, and I have a blue ball which has been launched to the right at a certain velocity. This is your classic projectile motion demo. The one thing to point out is that this horizontal motion of the blue ball has no effect on its vertical motion. They fall at the exact same rate. So what this idea allows us to do is break down complicated two-dimensional, three-dimensional problems, something like this, which if we wanted to mathematically solve for it, there are ways that I can do that in calculus to actually solve for what is the motion of the blue ball in terms of x and y. But there are easier ways to solve the problem in terms of the things we want to know. How far did the ball fall? How long did it take for the ball to fall that far? How far did it fly during that time? What is the maximum height the ball reached? What is the velocity of the ball before it hit the ground? All of those types of questions are ones that we would want to answer that are easier to break up these two-dimensional and three-dimensional problems into two or three simpler 1D problems. The nice thing about 1D problems is most of them are find the variables, find an equation, plug and chug, you're done. So let's look at projectile motion, because projectile motion is the classic two-dimensional problem that we use here on Earth. The vertical motion accelerates due to gravity, which is nice because gravity is always a force that acts straight down. Anywhere relatively close to the Earth's surface, that acceleration is always 9.8 meters per second squared. And when I say relatively close to the Earth's surface, I mean up to, well, actually probably several hundred kilometers. Even if you go up to the International Space Station and measure the acceleration of gravity due to the Earth, you find that it's pretty darn close to 9.8 meters per second squared. I think it's like 1% less or something like that, something insignificant. Generally speaking, in projectile motion, we ignore air resistance, which means that there's no acceleration in the horizontal direction. This makes life easy because automatically, if I know this is a projectile motion problem, I know the acceleration in both the vertical and the horizontal direction right away. So let's look at a quick example problem. And I'm going to place a cannon on the top of a hill that's 50 meters above the base of the hill. And we're going to assume that the land at the base of the hill is flat for miles. So we have like this, almost like this desert. You can think of the desert out in like Utah or something. And you have this plateau or this mesa that's 50 meters high. And it's going to launch down onto ground below it. You can also maybe think of the hill over by like St. Mary's launching into town in Faribault. The land in Faribault is relatively flat at the base of the hill. So the cannonball is going to launch, or the cannonball is going to leave the cannon at 100 meters per second at an angle 30 degrees above the horizontal, and we want to know how far does the cannonball fly. So some known and unknown variables. What I usually try to do in these types of problems is separate everything in terms of what's happening horizontally and what's happening vertically. First thing I can find out right away is what are the initial velocities. If I know it's 100 meters per second at 30 degrees above the horizontal, well, I know the x component is going to be 100 meters per second cosine of 30 degrees, and the y component is going to be 100 meters per second sine of 30 degrees. I know the acceleration right away. No acceleration in the horizontal direction or the x direction, negative 9.8 in the y direction. And so I'm using the negative sign here to say that down is the direction of that acceleration. One thing to point out about positive and negative signs when we're dealing with kinematics is that they totally depend upon what direction you've decided is the positive direction and what direction you've decided is the negative direction. That's a direction that I call, or that's a decision that I call an arbitrary choice or an arbitrary decision. We could say down is positive. All it means is that the initial velocity is negative 50. And we could actually do the problem perfectly fine. We don't know the x, how far does it fly? That's what we're trying to find. But we do know the y, how far does it fall? From its initial position, the displacement in the y direction is going to be 50 meters down, so negative 50 meters. One other thing that I don't know time. I don't know how long the cannonball is in the air. One thing to point out about most conventional projectile motion problems like this is that time is usually an important piece of information because it's what we would call a shared variable. It's the same in both the x and the y direction. So probably what I want to do is try to figure out time, which looks like I have enough information over here that I could maybe solve for time. And then once I know time, I'd have enough information to solve for x. So let's use some relationships. The relationship I'm going to use in both these is what I call the third toolbox equation, v initial t plus 1/2 at squared. The nice thing about the x direction is that a is 0, so that cancels out. Some inconvenient things about the y direction is that I end up with an equation that looks like this, and I want to solve for t. Unfortunately, this is a quadratic. If we solve it, negative y plus v initial t plus 1/2 at squared. And if we substitute some things in there, we get 0 is equal to 50 meters plus 50 meters per second times t plus negative 4.9 meters per second squared, t squared. Now, there are several ways you can go about solving a quadratic. One is to look to see if this is a perfect square, and I will guarantee you this is not a perfect square. The second thing to look for is, can it be easily factored? And I will guarantee you that this cannot be easily factored. Third thing you could do is do a process called synthetic division. It's not exactly the funnest process, and for a quadratic there are actually easier ways to solve it than synthetic division. The last two steps, graph it or quadratic formula. I would probably try to graph it first, plug it into your calculator, go online, find an equation graph or whatever you happen to do, and then find when does this equation, 50 plus 50t minus 4.9t squared equals 0? What are the zeros? You're actually going to get two zeros. One of them will be a negative value for t. That one doesn't make any physical sense in the context of this problem because that means that it happened before the cannonball was launched, since we're saying t equals 0 is when the cannonball was launched. And the other one will be a positive value. I've just saved the positive value 11.12 seconds. What I can then do is substitute it in for v initial t on the x side and get the cannonball will fly 963 meters. All right. So the next problem that I have is I have a particle that has an initial velocity of 3 I hat minus 4 j hat plus 2 k hat. And after 4 seconds, the particle has a velocity of 1 I hat plus 2 j hat minus 2 k hat. I want to know what is the average acceleration and displacement of this particle in unit vector notation. So we've got some interesting things here. We've got something that is a three-dimensional problem, and we want to find average acceleration for it. Well, average acceleration is v minus v initial divided by t. So what I could do is find the x component, the y component, the z component independently and solve those out. But another nice thing about unit vector notation is if I take this whole unit vector, well, here's my final velocity, 1 I hat plus 2 j hat minus 2 k hat. There's my initial velocity, and actually just substitute them in for v final and v initial. Substitute t in for t. Guess what? If I combine like terms, which I've done here, 1 minus 3, negative 3, 2 minus a negative 4, which would be like 2 plus 4, 6. Negative 2 minus 2 would be negative 4, and solve it out, we got the average acceleration in unit vector notation right there. Negative 5 I hat plus 1.5 j hat minus 1 k hat. Now it's worth pointing out that independence of motion thing, when I've done this in unit vector notation, I've already included that in this information. Now, one thing to point out here is that there's nothing in this problem which states the acceleration of this particle is constant. And so it might be difficult to then work through what the actual, what are some of the actual values in terms of how far did the particle travel, or how long, some of those other pieces of information might be harder to actually get. Displacement, we can use for displacement is average velocity times time would give me displacement. Well, I can find the average velocity by adding those up. What's going to happen is 1 plus 3 is 4, 2 plus negative 4 is negative 2, negative 2 plus 2 is 0, and so I end up with, well, all this would work out to be 8I hat minus 4J hat. Now, if I wanted to know in terms of, say, a magnitude, I could then use Pythagorean's theorem to find the magnitude in each of those cases. So sometimes working with these vectors in unit vector notation in terms of multidimensional kinematics can actually be easier than separating variables. This is another way that you can do this same type of problem, and we could have actually, if we wanted to, we could have probably done the Cannon problem that way as well and actually solved it out that way. So that's a quick overview of kind of 2- and 3-dimensional kinematics, how to work through some of those types of problems.